my sort of plan B. If it was cloudy, we might be lucky, but this will run for about 15-20 minutes, and we'll see what the sky's doing. So this is Comet Neowise. This was one of the early pictures I took. No, actually, it was last Saturday. I was here last Saturday. I started about 10 o'clock, went through until about 4 in the morning, imaging the comet and various other objects. But Comet Neowise, it really is a grand object. Probably one of the most spectacular comets since Hale-Bopp days. You all remember that in discovered 95, 96. The only other reasonably bright one we've had recently is Comet Connaught. This was 2006 P1, discovered by the Australian Rob McNaught out at Siding Springs. Now, this was a one day in this image here was, I think about the first week in January, we could see it very low down in the sky. It was heading south and it had just come out from conjunction from the sun. I got this picture over the sea at Branscombe Beach. Now, if you were lucky, when you actually went down and saw it in its magnificence in Australia, this is the extent of the tails. These structures here are called synchrones or synchronic bands. And they're all formed by little fragments of the comet breaking off and forming their own little tail. And you only really tend to get that with great comets. But we've also seen that with this Comet Neowise. You can see these little striae or these synchrones forming in the tail here. And this is the grey, the palely coloured, the dust tail, which is larger particles. And this is the blue, of course, the iron tail. Wonderful picture from General Raymond from the French Alps. And here you've got a disconnection event. This is what Lucy was describing about the solar wind. That will interact with the comet tail. It can cause these whole tails to break off and then start to reform. So you get a little sort of bubble in the tail. So one of the great comets that really got me into astronomy was my first view of a comet. This is Comet Bennett back in April 1970. I'll always remember that one. This comet was so bright, you could see it in the dawn sky. You could see it against a blue sky. That was just a 15-second exposure with, I think it was almost a Brownie box camera with the old Tri-X black and white film. So just recorded on black and white film for 15 seconds, you realize how bright that comet was. So this is a picture I took a week ago here in the Connaught Dome at the head of the comet. Although, of course, we love looking at the tails of the comet, don't forget to put your telescopes right on the nucleus, because lots of interesting things actually happen in the nucleus of the comet. So we call this the nucleus, but the nucleus is really the tiny little structure right in the center. In Hale-Bopp, quite a large nucleus, about 30-40 miles in diameter. We believe in Neowise, it's just about 5-kilometer size hard nucleus in the center. Around the nucleus, you get this called the pseudonucleus, the bright bit where the coma grows, and you get this dark structure through this is actually the shadow of the nucleus. So the sunlight's, of course, shining in this direction, and the darkness is the shadow of its nucleus. Either side of that is, of course, the bright comet tail. At the front here, we've got these like parabolic hoods. You can see these here forming, rather like the bow wave on a ship going through the water. And of course, we saw them very clearly in Comet Hale-Bopp and Hyakutake. So when you're looking at the head of a comet, look out for some of these other features. You'll see jets, you'll see little knots. Sometimes you see little bits falling off, running down the iron tail. Fountains and these parabolic hoods. This is a recent picture from the Italian Gianluca Marsi showing structure in the head of Comet Neowise. This was taken just a few days ago. So you can see these little shells. If you take a long exposure photo, of course, you get the nucleus of the comet all overexposed, but you can see the fine dust tail here of this comet. This is Comet Hyakutake back in 1996. But inside the pseudonucleus, there was a lot of activity. Using some high-pass filtered images through the same telescope here many years ago, this is 1996, you can see all these little jets coming out of the comet and running down this very narrow spine here. You can actually see little bits of comet falling off and running down it. Comet Hyakutake was a beautiful object. It also formed these shells, rather like we saw in Hale-Bopp. Well, they weren't as pronounced as the Hale-Bopp shells, but when you process the image, you can see these beautiful jets coming off the head of the comet. And there were 5 jets on Comet Hyakutake at the time. The dust shells on Hale-Bopp were very evident in any size telescope. But bear in mind, these shells were about 12,000 kilometers apart, and we saw about 4 or 5 of them leading off from the head of the comet. Now, how they were formed is this comet was spinning around at its axis in about 11.5 hours. Here's a jet sticking out for about 8,000 kilometers. Terry Platt did a wonderful video showing the jet rotating and these shells migrating out ahead of the bow wave. The other surprising thing about Comet Hale-Bopp, which nobody to my mind has fully explained, we had these curious stationary jets that appeared. Now, these weren't rotating like the comet. These were quite large features. There were about 5 or 6 of them that spread out, but they stayed in this position for many months. So here we are, October to December, and the jets were still there. So these weren't rotating with the head of the comet, but they were all part of the structure and the tail. So going back to last Saturday night, the comet was very low down in the sky when I started imaging. That was the first night it was visible in the evening sky, and the comet was literally 5 degrees above the horizon. So the computer wouldn't let me slew that low, so I had to manually override with a little joystick control. So I've now got the comet lined up. You can see only half the telescope is viewing the comet. Here's a little image of the comet on the screen. But what we did, we put our ALPI spectrograph on it. The ALPI spectrograph goes between the eyepiece and the camera. This is the main bit of the spectroscope. It has a little narrow slit, 25 micron slit in the end there, and a little like a star analyzer grating, diffraction grating behind that. And with that, I've got a spectrum of the comet. And you can see all these bright lines. The dark lines here are, bearing in mind the sky wasn't completely dark then, these are the Fraunhofer lines in our sunlight. These are the oxygen and water lines. You can see some of the Fraunhofer lines running back here. The comet spectrum is the bright bit going right through the middle. A very bright line there, some banded, what we call fluted lines here, another bright one in the deep ultraviolet. So we can put that spectrum into our software analyzer, which we're using here, which is RSpec. And we can see these, you can see on the spectrum below and a graphical representation above it. And you can see this very lovely bright yellow line. And when we calibrate it, we work out this is a sodium line. Lockyer would have known this as his D1 and D2 line. This spectrograph is not powerful enough to split this line in two. The sodium does actually have two lines very close together. Robin Ledbetter succeeds in getting a high resolution spectrograph showing this split into two. So that's a very bright yellow line here, which is due to the sodium. Now this is an interesting photograph taken by Andy Wellington, showing a very red tail adjacent to the blue ion tail. So jury's still out on this, but we suspect this is due to the sodium line. It's quite rare in comets. We saw it in Comet Hale-Bopp, and it generally only shows when a comet is near to the sun. It needs plenty of heat to form a sodium tail. First time this was discovered, actually, was the Isaac Newton group of telescopes who imaged this sodium tail in Comet Hale-Bopp. It's this very straight, narrow feature running out at this angle here. So they say Hale-Bopp's sodium tail consisted of neutral atoms, not ions, extended to some 50 kilometers in length. The sodium tail of Comet Neowise has also been recorded by the Planetary Science Institute's facility. Here is the normal, this is a color-coded image showing the normal dust tail of the comet. And this one here in sodium light shows the rather narrower sodium tail. This beautiful image here was actually done with just a Star Analyzer 200 showing the lovely sodium tail of the comet, and this is the zero order image. So you can see this, the sodium tail is offset and runs slightly to the left of the main dust tail. So working away to the left of the spectral image, you come to these bands here. I've labeled C2. That's another one here, the C2. These are the so-called Swan bands. They were discovered by the Scottish physicist William Swan, who first studied, he was analysing the spectra of the butane flame, and he came across these fluted bands here. But you also see them in carbon stars and if you're burning hydrocarbon fuels. So now we come right to the far left in the spectrum. This is the blue end, the indigo region of the spectrum. And this one here is labeled CN due to cyanogen. There's general few words about the blue end of the spectrum. Indigo is, of course, a shade of blue. This is the closest we can get on a computer screen to the color indigo, apparently. And it was Isaac Newton who named this color of blue when he divided up the spectrum into the 7 colors. And the indigo range is between 450 and 420 nanometers. The name of the colour indigo originates from the plant. Indigo, of course, is a dye made from the plant used to dye cloth, which they use to dye blue jeans. So really they should be called indigo jeans. So some indigo colours you're probably familiar with. There's some grapes, blueberries, eggplants, and of course the night sky mid-even just before it goes completely dark. So back to our cyanogen emission line. You can see right here, this is the actual wavelength of light here is actually invisible to the human eye. But cyanogen is a chemical compound with the formula CN2. It forms this triple bond between nitrogen, and this is typical cyanide bond, the N triple bond C. Cyanogen was first synthesized in 1815 by Gay-Lussac, who worked out his empirical formula and named it. I've got a vague remember of Gay-Lussac's law in A-level chemistry, but I can't remember what it is. Probably something to do with pressure and volume, I think. But he coined the word cyanogen from the Greek words kaianos, with blue, and genoa, which is I create. In 1910, just letting someone in, Geoffrey Legg. In 1910, an analysis of Halley's Comet showed that it contained cyanogen in the gas tail, which led to a public fear that the Earth would be poisoned if it passed through the comet, when it was due to pass through the comet's tail. And of course, this is Halley's Comet in 1910, and this is the little cartoon showing the end of the world, fin du monde. Interesting here, 1910, of course, is when the Wright Flyers, this is Frank McLean's Wright Flyer, right about that era. And this little newspaper cutting here, deadly cyanogen gas does not travel through the water. So to escape the comet, hire a submarine boat, fill it with 3 days edibles and drinkables, and go underwater tomorrow. The deeper the spot, the better. Stay under for 3 days, not even poking your nose above for 1 moment. At the end of that time, if nothing happens to your submarine, the cyanogen gas in the world will have spent itself. Then, if all the people in the world have perished under the deadly gas, you can claim the world for your own. If they are not dead, perhaps you can stand the laugh. So, a word about Prussian blue. This is a modern synthetic dye which was discovered completely accidentally. I think it was some Berlin scientists who were trying to produce a red dye, and they ended up with a blue dye. But it's called Prussian blue because it was used to dye the uniform coats of the Prussian army. Over the years, it's been called other things as Berlin blue, Parisian blue, or Turnbull's blue. But despite the presence of cyanide in it, the pigment is not toxic to humans, which is just as well. Since 1958, the name Prussian blue in Crayola Kales has been replaced by midnight blue, since Prussia no longer exists. Prussian blue is a very important pigment for artists. In the early 18th century, artists didn't have an affordable or stable blue pigment to use, and they used ultramarine, which was extracted from the stone lapis lazuli, but that actually as a mineral was more expensive than gold. And most of that originated from Afghanistan. Famous artists who have used Prussian blue include Gainsborough, Constable and Monet, Van Gogh, and of course Picasso in his blue period. He must have used a lot of blue paint. And of course this is Van Gogh's famous Starry Night, made with Prussian blue and hence directly linked to the colours of comets. So where's the comet tonight? Well, we're actually in the paws of the Great Bear. I took a picture of it last night here. It's now right in the paws of the bear, and it will get higher over the next few nights. It's still reasonably bright, so you'll easily spot it with the naked eye for the next week or so. So if you haven't seen it yet, don't worry, there'll be plenty of other chances. This is the picture I took, this is probably about a few days ago. Here's the dusty tail, and you're just beginning to see the blue iron-tail. And this is a picture I took last night, drawing a gap in the clouds. This was a 300mm lens. You can see the lovely dust tail. Can't quite see the synchrones in the tail here, but you can see quite clearly now the blue iron-tail. This picture also last night. The comet's now high enough, I can get it from my garden. Of course, there are a lot of clouds here, but you can see how long the tail is. I think Nick James measured it to be about 15, 18 degrees. So that's, you know, it's a great big large object. You can see why the ancients were fearful of these broom stars, because they can be quite huge in the sky. This is, of course, the paws of the Great Bear, and so, you know, this is really getting a large sized object now. And of course, it's going to be closest to us on July the 23rd, so it's actually going to get probably bigger and brighter. So, happy comet hunting. What I was going to do next, this is plan B, still too bright to see any planets yet, but we can show you some image I took last Saturday of Jupiter. This is a processed image of Jupiter and its little moons. You can see the dark belts and the brighter zones. That was taken through the Connaught. This is Saturn. Of course, but all the I'll play some little videos of these videos I've processed, but of course, both Jupiter and Saturn are very low down in the sky. You probably see them next to the Milky Way in the south. So the seeing conditions aren't brilliant, but you can make out, just to make out the Cassini division between ring A and B. And this is a picture of Mars. Mars, of course, is a morning object. You can make out the polar caps here, and I think this is the sinus sebaeus, this long structure here. So I think that was the end. Yeah. So what I will show now is a few videos to show you what it actually looks like. Had it been clear, we were imaging, this is sort of thing that we would have seen. Let's see if this will run. So that's an image of Mars. You can see it jumping all around. That was taken with this little camera. Can you see that?
No.
No.
Not the little camera.
Oh, right. Haven't I got my video on? I'll show you. I'll just play these videos and then we'll... Southern Mars. I actually need to go back. That's Saturn. So that's a typical video you'll get. I was taking about 20-second videos and processing about 500 or 600 images or stacking them together. Oh, another one of Saturn. There should be some Jupiter ones here. Yeah, it's Jupiter. The other effect you can see, of course, when you're imaging the planets from the low down is a traffic lights effect. You can see it's red at the top and blue at the bottom. This is our atmosphere spreading out, acting as a prism and spreading out the light. You can correct this in processing software. So that's it.
Thank you, David. That was really good.
Yeah.
I'll have a look now and see if I can see Jupiter. It's probably still a bit bright, but you never know. I'll fire up the computer and the telescope and we'll slew to it. So just chat among yourselves. I'm going to put my earphones down.